is expanding quantum field theory using affine quantization. The lecture will include what is affine quantization, discuss eliminating nonrenormalizability, and an important and essential Fourier transform. We have basic variables, P and Q on the real line, and they are getting promoted to quantum operators, capital P and its adjoint, capital Q and its adjoint. And this is a commutation relation here. Here we have a coherent state, P comma Q, e to the minus I little q capital P, e to the I P little p capital Q, and a fiducial vector omega. If omega here and here give us the expectation value of capital Q and IP. Both of these are Hermitian or self-adjoint operators. So we have a real one here and an imaginary one here. And with a 0, that means both of those expectation values vanish. Higher powers of these variables are going to be proportional to h bar. Now, Dirac has made an important remark. Having quantum functional with classical variables and a classical functional with classical variables requires Cartesian coordinates so that, and in order to obtain physically correct operators. Dirac himself did not do that, but here we have a quantum function of capital P and capital Q in expectation values in this coherent state. This gives us something that looks like a classical Hamiltonian, but it has probably some h-bar dependence. These unitary operators come along and they give us capital P plus little p, capital Q plus little q expectation value in the fiducial vector. That means, let us take a look at this as if it was a polynomial. So P plus P to first power, expectation here would be give us little p, and this term would disappear. The square of this would have a little p squared, a mixed term between P and capital P, that would vanish, and capital P squared would have some h-bar dependence. That means we can separate into this quantum functional, no h-bar, and PQ's there, and the rest of it is has an h-bar dependence with P and Q. Now, if h-bar went to 0, this would disappear. This would be h-bar independent, and any h-bar that lived here before was gone. And that means we have attained what Dirac wants. We have the quantum function and the classical function being equal. Now let's focus on getting the Cartesian coordinate. If I put a phase factor up here, e to the I little phi, e to the I f of P and Q, that would disappear here because this one would be the opposite of that one and they'd disappear. So it's not there and not there, not there. And that means it's not physically important or relevant. Here is a way to get metrics. Take a differential of a coherent state and take its absolute square here. Now that's going to depend on that fiducial vector here situation with its phase factor. Well, here is the Fubini-Studi from the early 1900s method of canceling that phase factor story. And so now what we get is a truly physical story which has omega to the minus 1, dp squared plus omega dq squared, and that does have Cartesian coordinates. This is canonical quantization that we got of a flat surface, and I'm going to use a strange phrase, a constant zero curvature. And you will see this kind of statement again. Here is something familiar to you. We have classical physics that run over the PQ coordinates run over the real line. Here is the classical action functional to give the equation to motion. Here is the promotion from classical to quantum of the favored variables. And with Schrödinger's representation, Q goes to real variables over the whole line, and capital P becomes a differential term. I underlined it because it will come back later. And Schrödinger's equation is the derivative of the wave function with respect to time, the Hamiltonian depending on the momentum and the position and the wave function, and this is the standard normalization factor that it must be finite. Now, here's an example problem. We're going to force Q to be positive. And this is the harmonic oscillator, P squared plus Q squared. Nevertheless, we're going to do it for Q positive. Here again is our classical action functional for this particular case. Now we have something strange or difficult. Capital P is not equal to its adjoint here. Little q, and it big goes to big Q, and it is okay. It is equal to its adjoint, but of course now it's positive. This fact that we have two distinct momentum here leads to multiple Hamiltonians. For example, P times P dagger plus Q squared divided by 2, P dagger times P plus Q squared divided by 2. These are two distinct Hamiltonian operators, both of which would go back to the classical form here when H bar went to 0. Indeed, we have different spectra. This one right here gives this spectra with even integers, and this one right over here has odd integers. And since they both go back to the same classical variable, we can mix these two together, so we have an increasing numbers from the even, and then the odd, and then the even. This is surely canonical quantization, which fails. Now, let me introduce affine quantization to you. We're going to study it first with P over the real line, but Q positive, which we could not work with before. Here is a reminder of the last slide. P not equal to its adjoint. Let's find a new variable to get for P. I introduced D, the dilation variable, which is the product of P and Q. Its operators would be P dagger Q plus Q P divided by 2. That gives us the quantum operator dilation operator, and it is self-adjoint. Notice this is the new related quantization related things here. And this looks like a Lie algebra. In fact, the Lie algebra of this form was done in the last 1800s for the affine group. And with that, we have given that name because of this form. We have new coherent states, P semicolon Q, to distinguish them from the former ones, little p and capital Q, natural log of Q, which is okay because Q is positive, and capital D up here. We have a new fiducial vector, which is sitting here and here. Expectation values of this term would be real. Expectation of this term would be imaginary, and both of those would be 0. So that means that Q is equal to 1 in this expectation value, and D equals 0. Let's do another favored affine coordinate story here, like we had before. Here's a quantum Hamiltonian now with D as the momentum-like variable. We call it the dilation operator, and capital Q here, again between the two new coherent states. Here is our Hamiltonian function that looks classical, but it has some H bar in it. Here is it happens when we bring these unitary operators together. We get capital D, we have little p, little q, and capital Q. None of these three depend on H bar. This one depends on H bar. Using the polynomial formula times things we did before, this gives us a quantum functional of classical variables and no H bar dependence, plus an extra term with H bar dependence and its classical variables. Let H bar go to 0, this one disappears. This one never had it, and any H bar dependence here is gone. That's part of what Dirac wanted us to do, but let's now see if he gives us Cartesian coordinates. Here is the formula that we used before, now with the new coherent states. This would have a phase factor. This is canceling the phase factor. And the result is b to the -1 q squared dp squared plus b q to the -2 dq squared. That is no Cartesian coordinates. However, it is a very important expression because it leads to constant negative curvature. And in fact, this is the magnitude of that negative curvature for this thing. It means if I had a space which had its own constant negative curvature, this would be the ones that would give us this metric. Now, just to get some clarification there, there is something called the constant positive curvature, and that is coming from the spin variables, and that is going to be a sphere. A sphere here in 2 dimensions makes a circle, and in 3 dimensions, it looks like the surface of a basketball or the surface of the moon as we see it from the Earth. Anyway, that takes care of the positive, the 0, and the negative curvatures, all of them. Here is a rich slide. We're going to have a lot to say about it. So here is the problem where Q is positive. Here is our Hamiltonian. It's the same as before because P squared is there, Q squared is there, and Q squared takes it away. But PQ is our new variable, Q squared there. Here is the classical action functional, P times Q, Q dot divide by Q. So that's simple, nothing new there. And this is the new Hamiltonian formula. I remind you that we have the P is still not self-adjoint at all, but P dagger times Q is equal to P times Q. That means we can take our dilation variable when promoted to P called PQ plus QP divided by 2 and still be D which is self-adjoint. Now, let me explain carefully why this is the case, and let's understand what is the difference between P and P dagger when they are not the same. Let's make it a little integral between little a and little b of g star x f of x dx. And this prime here means derivative. That's the derivative with respect to x of the whole thing. Well, before we give the answer, let's break it into two parts. G star of x prime, so that's the derivative times f, and g of x star times f of x prime, so that's the derivative of the f. This answer to that is, of course, g star of b, g of f of b, minus g of a and f of a. Now, this extra part here is a nuisance to us. We want to get rid of it. So we forcefully say f of 0 equals 0, f of b rather equals 0, and f of a equals 0. And that means these g's can be anything they want, and we've gotten rid of this term here. Well, that looks kind of suspicious to us. So let's take an example here. Let's take it from A to B. Again, we have this situation here and here. Suppose we have situations in which, let's go back up to the next slide here, where are going from A to B. If B was in plus infinity, then this function would fall off by itself and g would be 0 by that. If a was minus infinity, then that would all fall off for a. So that's the way we would get these would have o's as well. In fact, we would have, for our case here, we have x from going from plus infinity down to 0, and we want to have both g's disappear. Well, the g of b will disappear because of the infinity, but this one would be 0 if we could help. All we need to do to help is to add an extra function, little x, into there, and when x equals 0, we have our x 0. So that's the way P and P dagger are, and how it affects when I put that x in front. This is like the Q in front, the P dagger and the P will be the same. Schrödinger's representation is Q going to X for the positive line. You remember we're doing this in the positive side. And D is the differential equation for the dilation operator. Schrödinger's equation then, again, derivative of the wave function with respect to time, Hamiltonian of the dilation operator, the position operator, and the wave function. That's the not the normalization, but the criterion that we need for it. And here is a new feature. We have d of x to the minus 1/2 equals 0. Well, we're going to see other things like that coming along, and I give it a name, a master equation, and I did label that as me. M-E is me. Now, let's see if we can solve the half-harmonic oscillator that we could get canonical quantization could not do. I emphasize again, this is our basic variable d, which is p times q. Q is in positive here. Q could kill this whole thing if it was 0, because then that would be 0 for d and p could not help, but we're not including 0 here. The classical Hamiltonian then reads d squared over q squared plus q squared divided by 2. The quantum Hamiltonian capital D and Q, the dilation operator, and Q is here. Capital D, Q to the minus 2, D plus Q squared, a mimic of these formulations here. Schrödinger's representation, Q goes to X on the positive half line. Here is our dilation operator in this differential part. Now there's some analysis that goes along in here, and that this Hamiltonian function is now written here in terms of these variables, h bar squared times 2 derivatives, 3/4 times h bar squared divided by x squared plus x squared over 2. So that's our new equation of motion for the half harmonic oscillator. Of course, if this term in the middle was missing, that would be the traditional full harmonic oscillator. And the spectrum for that is here, h bar, and all the positive integers, including 0, plus a half. Well, with you now including this term here, in this, the eigenvalues are 2 in front of that, and that 1/2 over there is changed to 1. But it again has equal spacing of eigenvalues, just like these were equal spacing. That, to me, gives a partnership between these two variables before. In fact, Madame Guba has written about this topic in archive number here, and I will give several numbers of archive at the end of the lecture relevant to this lecture. Here is our first classical story, classical field theory. We have a little star here because we're going to have some initial quantum issues as well. Let's have a momentum here, pi of x, phi of x for the field, x in an s-dimensional space, all of for over real whole lines. And we're going to talk about the canonical quantization on this page. Here's a typical classical Hamiltonian here, pi squared, gradient of phi squared, a mass term phi squared, and an interaction term here with a coupling constant g, and little r is my power of interaction term. S is the number of spatial dimensions here. Add 1 to that, and this becomes the number of the space-time dimensions. Well, it's been worked out that when R, which is the power of the interaction term, is less than 2n divided by n by 2, that leads to renormalizable behavior. However, when R is greater than or equal to 2n over n minus 2, that leads non-renormalizable behavior. This issue has been studied by Monte Carlo calculations for the field. Number up here, R, is the power of interaction, and n is the space-time dimensions. So if we have phi to the 4 and 3, that's 2 space dimensions, 1 time, and power phi, that has an arrow up. An arrow up means it is not free, not free. In other words, the presence of G is felt in that story. On the other hand, phi 4, 4, that's 3 space dimensions and 1, the one we live in here, in phi to the 4 is arrowed down. That means it's free. In other words, although G is positive and present in the calculation, it acts as if it is absolutely absent, and just like a free theory. And here's another wild one, phi to the power 12 and 3, again, is a free answer. I attribute that to domain changes. Domain is how many what the number of functions you can write in here and still have a finite answer. That goes when G equals 0. But if you introduce the interaction term here, that could reduce the number of functions you can put in here and still have positive, not finite answers. So that domain could be possible bigger than that. So the domain difference is perhaps the cause of the non-renormalizable behavior. Now, here is an affine story in which we multiply again a momentum and a coordinate. So it's phi of x and pi of x, and phi of x gives us our affine field. Phi of x must not be 0 because, as we said before, kappa would be 0 and pi could not help. And this is the affine quantum page. Here is the same Hamiltonian written in these new variables. Kappa squared divided by phi squared. Well, that's clearly going to look like pi squared by itself. The derivative of phi squared is the same, mass of phi squared is the same, interaction term is the same. So that means the R term is exactly what it was before, the power of the interaction term. The N is there for the number of spaces and 1 for time, that's the space-time dimensions. And the Monte Carlo calculations of the same kind have all been showing arrow up, non-free. So here it is, up here, and up here. They are non-free, 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 in meaning that G is playing a role in the story. And I consider that to be a legitimate pair of classical variables. One more time, let's take it affine and canonical together. Here in the top of the page is the affine story. Here is the affine field, the product here. Again, don't include 0. Have this Hamiltonian for the classical terms. And now watch. Phi of x cannot be 0. If it was 0 to the minus power here, that would be infinity, but that's forbidden. And G and phi by itself, which would be terrible stuff for this things here, could not be become infinity. So it's bigger than 0. So we have this expression 0 less than this term and that implies that 0 bounds this term and infinity bounds this term. So that means this is truly renormalizable. Again, for the canonical story, the usual procedure is that you take the interaction term and bring its number of phi's to a different power. Over here, here is the traditional part that lives in the Hamiltonian. And this there, if you doubled the phi by itself, that would make this 4 times bigger. They want the same number over here, 4 times bigger, and that's what this is here leading to. Nevertheless, those are the formulas here. R less than this gives us the renormalizable, and R greater than that gives us the non-renormalizable, and that is how canonical quantization compares with affine quantization. Now, let's talk about quantum field theory. We're going to take the Schrödinger representation so that this operator becomes an ordinary function, again, not equal to 0. The affine operator looks like this: phi times the derivative, derivative times phi. And we have some me terms here, kappa acting on phi of x to the minus a half gives us 0, or if a product of over all the phi's by themselves, we still get 0. In the Schrödinger representation, the kets of Hilbert space can become just ordinary functions. And here's one of the examples, and here's a second one of the examples of here. We're going to use those wave functions as we go. Now, selected wave functions here, x and y, are in the s-dimensional real line third. Here, capital phi is a wave function given by this product of integration of some term here with our wave function here. Similar for capital psi, similar to that. And the where the connection between those two together is given here. Now, finally, we're going to look at a regularized representation story. Capital Z lists the integers from minus infinity to plus infinity. We have S of them for S dimensionals. Little a stands in front as a distance thing, and we'll call those factors K. Here is a two-dimensional example of this. Little a is the distance between these rungs, and every point here, point here, point here, point here are part of the K family. So the Schrödinger representation, phi K operator, go to phi K, kappa operators go to this differential equation. And here's some me terms. In fact, now is the time for us to look at this me term and prove it for yourself. Phi, forget their k's at the moment, kappa of phi to the minus a half. Bring that phi to the minus a half up here. That gives us a phi to the plus a half. Take the derivative, that becomes plus 1/2 phi to the minus 1/2. Now bring it up to here as phi to the minus a half. That makes minus 1/2 phi to the minus 3/2. But then when I put it a phi on top, it's minus 1/2 phi to the minus 1/2, which cancels and gives us the 0 here. Here are some selected regularized wave functions. Capital phi, again, product here in a regularized now way, times e phi to the power here, psi, capital psi for the wave function here, and here's the overlap between them in the wave in the equations. Now, what have we found? We found Schrödinger's equation for a quantum Hamiltonian of the affine operator and the Schrödinger form of the phi. Let's take a solution such that it's regularized and normalized and actually bound absolutely and squared. And here is the functional form of all that. And that gives us 1 because of its normalization. Now we introduce our Fourier transformation. E to the I, f sub k, phi sub k, and that gives us the transformation of that function, capital F for Fourier of little f of those. If all the little f's are 0, then that number becomes 1. And here it is again, f of complete zeros is simply here is the normalization. So it's the 1. And now we're ready to set up for limiting a to 0. Here we have a typical wave function that we want. Here is its normalization, which we know now is called f of 0 as well. And I rewrite capital F of little f in a helpful way. we have one here and we have one here. So this one here is this one, and this one here is all of this stuff. So this equals that. That means that that one is canceling that one, and this minus to get together to make the plus term for the Fourier transformation. Now, when we take a towards 0, this is going to be tiny, tiny, tiny. Indeed, it becomes an exponential in this continuum limit of a, e to the minus little b integral here. B was always there to make the dimensionless story. And here we have 1 minus e to the I 2 pi f of x lambda absolute W of lambda quantity squared lambda inverse d lambda. Now that could diverge by itself, but it's sitting between 1 and something that if lambda went to 0 would be 1 and cancel that. This is a Poisson distribution in real life. And here it's also an example of central limit theorem, I believe. So here is our Fourier transform function again. If G equals 0, that means if the coupling constant to our interaction term is 0, our Hamiltonians are full of quadratic fields. When those are considered in a Fourier transformation as a Gaussian, the answer becomes a Gaussian. But this is a situation in which our case, when G goes to 0, it is not a Gaussian. This term may look like e to the minus lambda squared, perhaps with some constant there. That could be the residue of the Gaussian, but it's not in any form making a Gaussian of that. So we have a legitimate pair of quantum variables, kappa and phi operators, Schrödinger representation, not equal. And again, we use the trick. Phi, when this is 0, this cannot be 0. If it was 0, that would become infinity. And infinity here is not allowed because that all the other fields would feel it. So it's bound here. And this particular relation implies this relation. This was a good term for us, even if it can have some zeros along the way here, but that's not final. And again, we have no non-renormalizability to worry about. What has led to the final affine quantization result? Well, we have a normalization, as we discussed, of the regularized form. We have some components I like to point out. Differential of a absolute of a phi here, up to the power 2bas. I remind myself that little b is the number about 1, which makes this dimensionless. That differential brings these down there and gives our expressions that we've seen before here times d phi k. This is going to go to 0, a goes to 0, a goes to 0 here. Now, if this was a minus term here, which also goes to 0 at the same place, but that would be a minus here, that would be bad. If this was a minus, this would become a plus, and that's bad. So we're very happy to have this positive derivative. These are well-behaved aspects as well for here. Here's our Fourier transform in the regularized form. And here is our Fourier transform in the continuum form. And the bonus treasure from all of this is that there's no non-renormalizability. Now I'm going to open the doors and show you a new example. Let's take a classical Hamiltonian gradients term, mass term, and a new kind of interaction term. G is our coupling constant, but now instead of phi x to a power, we have phi x minus 1 to a power. That means we have +1 and -1, which are forbidden here. Nevertheless, we use that in our new affine variable, kappa times not 5x as before, but times this quantity right here, 5x squared minus 1. This illustrates that the affine formulation can find a way to modify itself to help deal with very, very different possibilities. So again, that's in this store, that becomes kappa squared times 5 squared minus 1 to the -2 power, plus the other terms as before. So we do not want to have this to be 0. That would be infinity. So, and then to quantize that by the Schrödinger representation technique, we have our gamma affine operator times the momentum and times this exponent to the and this to the times kappa. The operator for the Hamiltonian is kappa 5x to the -1, 5x squared minus 1 to the -2 power kappa, and all the rest terms are the same. Here's our interaction term, g to that power. And all of that requires that phi squared minus 1 must not be 0. And that leads to the fact, if it can't be 0, then it's less than infinity. If phi is infinity, that would be 0, but phi was not chosen to be infinity. That relationship implies this very relationship over here. And again, we have one, no normalizability. I wish to thank you for this and open a channel. Another Fourier transformation is desired to see the results in proper coordinates. We have capital F of little f, but I would like to see the functional form back in this phi here. This task is open for others to contribute. Perhaps that kind of Fourier transform has already been made, and I would love to hear about it. And there is my suggested publications for here. Number 1 deals with what the affine quantization rules are. Number 2 is about the half-harmonic oscillator. So here's the harmonic oscillator, and here's the fact that Q is positive. Number 3 deals with the phi raised to the 4th power and with 3 plus 1, 3 space dimensions and 1 time dimension. And a more recent field, which is quantizing more fields than we've talked about, this is a vector field, phi as a vector field squared minus 1. And what does that make? It doesn't make points 0, it makes circles to be a 0. And it's interesting in this particular there. I offer you comments on my preferred email address, but again, I suggest please no political emails.